Okay, hi everyone. So in this video, we're going to be going through some calculations for how to determine the eigenvalues and eigenvectors given a matrix. Eigenvalues and eigenvectors. Okay, so just a quick recap, um, where these things come from and how to determine them. So eigenvalues and eigenvectors come from trying to solve what is called the eigenvalue problem. So in all of this, A is a square matrix, n by n matrix. So these things only exist for square matrices, right? Um, a non-zero vector V such that A V equal lambda V is called an eigenvector of A, and lambda is called an eigenvalue of A. So first thing to note is that the eigenvector has to be non-zero. So you're not allowed to pick the zero vector because, again, the main equation we are looking at is this: AV equal lambda V, or sometimes they use X, AX equal lambda X. Okay, so this V here is the eigenvector. And this lambda here is the eigenvalue. So when sometimes we put these two together, lambda with a corresponding eigenvector, when we put these two together, this is called an eigenpair. And how to think about this is anytime you do this, so this is a matrix multiplied by a vector. So this vector is a column of numbers. So anytime you do this multiplication, that gives you a new column of numbers. What the eigenvector equation is saying is that when you multiply this vector by this matrix, the output is the same vector, but it is just scaled. It's scaled by a factor of lambda. Now, maybe lambda could be negative in that, that means that the vector is just switch directions and it's scaled by the magnitude of lambda. This lambda could also be a complex number. So eigenvalues could be complex numbers as well. So all of this is in details in the course notes, but I'll just go over the basics that we need to do the calculation. So to find the eigenvalues of A, we solve for the roots of the characteristic polynomial. So P(A) of lambda, this is a polynomial of degree n. N is the size of the matrix. And what this is, in order to get this polynomial, we take the determinant of A minus lambda by the identity. Okay? And we of course solve for the roots. Roots mean when is this polynomial 0. This polynomial we call the characteristic polynomial of A. So when we solve this polynomial, if A is an n by n matrix, this polynomial will be of degree n, so an nth degree polynomial. And we of course know that a polynomial that is nth degree has n roots. Okay, now these roots may be repeated. It may all be different. Some may be complex. We don't know. okay? But the roots will be the eigenvalues. Now, for each of these eigenvalues to get a corresponding eigenvector, so for each eigenvalues, there are many eigenvectors associated to that eigenvalue. All of those eigenvectors live in a space called the eigenspace. So all the eigenvectors corresponding to an eigenvalue, so a fixed eigenvalue lambda, all the eigenvectors associated to this particular lambda live in a subspace called the eigenspace, right? And sometimes they use like a E, sometimes they use like fancy E, then they do like fancy E of lambda. And where this vector space, this subspace, what it is it's just the null space of this matrix, A minus lambda I. So what you will do, for each lambda you find here, each root you find, you will form this matrix, A minus lambda I. So if you find 3 different lambdas, you form 3 different matrices. For each of these matrices, you then determine the null space of. The null space we know is a subspace. That subspace is where the eigenvectors live. Okay, so this we know is a subspace. And the dimension is the nullity of A minus lambda I. Right, the dimension of the null space is, what we call the nullity. Now the number of times an eigenvalue lambda is repeated, so because when you solve for the roots of a polynomial, you will get repeated roots, and that root might be repeated 1 time, 2 times, 5 times, we don't know. The number of times that root is repeated is called the algebraic multiplicity of lambda. Of lambda, right? And sometimes we say AM, algebraic multiplicity of lambda. The dimension of the eigenspace of lambda, remember I call it the nullity. So this guy is given a name. Sorry, the the dimension is given a name. It's called the geometric multiplicity of lambda. So the dimension of the eigenspace associated to that lambda is called so this is a number. It's a dimension of a space. It's called the geometric multiplicity of lambda, Gm. And there's a result, right? There's a theorem, it's in the notes, that says that the geometric multiplicity is always less than or equal to the algebraic multiplicity. Okay, and of course these values must be bigger than 0. So if the algebraic multiplicity of an eigenvalue is equal to 1, the only possibility for the geometric multiplicity, which is a dimension, is that this is equal to 1. If the algebraic multiplicity is equal to, let's say, 2, if you get some repeated root 2 times, then you have 2 possibilities. Either the dimension of that eigenspace is 1, or it could be 2. We don't know. You have to we have to find it. Okay, so what we're going to do now is some examples where we're given a matrix. We want to find the eigenvalues. By first, we will form this characteristic polynomial, and then we'll solve for the roots of it. Then for each of those eigenvalue, we will then figure out what this space is, the corresponding eigenspaces, and maybe we'll generate a vector in this space, a non-zero vector, and that will be an eigenvector corresponding to the eigenvalue lambda. Then we could also say what is the algebraic and the geometric multiplicity of that eigenvalue. Okay. So the easiest example is, what if I take as my matrix the identity, the n by n identity matrix, right? Notice what is the eigenvalue equation again? It's a what was it? It was a v equal lambda v, right? But if a is the identity, then this is the identity by v equal lambda v. The identity by any vector v is the vector. So v equal lambda v. Therefore, lambda must be equal to 1. So what I'm trying to say here is that this matrix only has one eigenvalue. It's 1. And for that eigenvalue, so for lambda equal 1, if I plug lambda equal 1 in this equation, I get, so for that eigenvalue, I get the identity by a vector equal lambda, which is 1, by the vector, which is the vector. Which vector satisfies this equation? INV equal V, which non-zero vector? Remember, the eigenvector cannot be 0. But this holds, right? This equation holds for every non-zero vector, right? So for this lambda equal 1, every non-zero vector is an eigenvector. So when you take the n by n identity matrix, that matrix only has one eigenvalue. It's 1. And what are the corresponding eigenvectors? All vectors, all non-zero vectors are eigenvectors. Okay. In fact, the eigenspace for this lambda, which will be eigenspace for 1, is simply well, it will be the entire space. It will be in this case it's Rn. Right? It will be the null space of A minus lambda I. So it's I minus lambda, which is 1 times I, which is the null space of the zero matrix, which is the entire space, right? Which is Rn. So let's say we're in Rn, right? Okay. So the eigenspace is the entire space, Rn. Right. So maybe I should have said this is a n by n matrix over R, and V is a vector in Rn. Right. So the eigenspace is the whole space. The algebraic multiplicity of lambda equal 1 is, how many times it's repeated? Once. So it's of course 1. The geometric multiplicity of lambda equal 1, what is the dimension of this eigenspace? What is the dimension of Rn? What is n? Oh no, it should be the null space, or it should be geometric is not supposed to be n. Let me see. Oh yeah, sorry, I made a mistake here. The algebraic multiplicity of lambda equal to 1 is not 1, it's n. Because it's lambda equal 1, but it's repeated n times. And the reason for that is because the characteristic polynomial, right? This characteristic polynomial is an nth degree polynomial. So it means it has n roots, right? So lambda equal to 1 is the only root, but it's repeated n times. Yeah. So lambda equal, the algebraic multiplicity is n. The geometric multiplicity is n, right? Because it needs to satisfy this property, right? So the algebraic multiplicity was n. Lambda equal to 1 is repeated n times. That root is repeated n times. Okay. So that's a simple example. That doesn't require much calculation. Let's do one that has a calculation in it. Let's say A is given by 1, 2, 2, minus 2, right? And this is a 2 by 2 matrix with real entries, okay? So I want to know what's the eigenvalues, a corresponding eigenvector, what's the eigenspace for each eigenvalue, what's the algebraic multiplicity, geometric multiplicity, and so on. Okay, so the first thing to do is to form the characteristic polynomial. So form PA of lambda. So that is the determinant of A minus lambda I. So it's the determinant, so you know that's given by these two vertical lines. So how to get this matrix A minus lambda I? It's the same matrix A, right? So I write back the same matrix A, and then I subtract lambda from the diagonal, right? So subtract lambda from the diagonal entries. Now this determinant, you know how to do the determinant of a 2 by 2 matrix. It's this one by this one minus this one by this one. So it's 1 minus lambda by minus 2 minus lambda minus 2 by 2. Okay. So let's expand this one and see what we get. So this is minus 2 minus lambda plus 2 lambda plus lambda squared minus 4. So that is lambda squared. 2 lambda minus lambda is lambda, right? Minus 4 minus 2 is minus 6, right? So this will be, I think it will be lambda minus 2 lambda plus 3. Lambda squared, 3 minus 2 is 1, 3 by minus 2 is minus 6. Yeah. Okay. So this implies that the roots is when the characteristic polynomial is equal to 0. So the roots are lambda 1 is 2 and lambda 2 is 3. Right? So the eigenvalues are 2 and 3. And how many times are they repeated? So right away we could write down the algebraic and the geometric multiplicity. So the algebraic multiplicity of lambda 1, how many times was 2 repeated? It was once. It was 1. And the algebraic multiplicity of lambda 2, how many times was 3 repeated? Once. So is 1 again, right? And since we know that the geometric multiplicity must be less than or equal to the algebraic multiplicity, but the geometric multiplicity is the dimension of a vector space, and it was not going to be the zero subspace because an eigenvector cannot be 0. So it's going to be strictly positive. and it's a dimension, so it's a whole number. It's a non-negative whole number. So what whole numbers are there between strictly bigger than 0 and less than or equal to 1? Well, it's 1. So right away we know that the geometric multiplicity will be 1 for each of those um spaces, right? So right away we don't even need to work it out. We could just figure it out. So the geometric multiplicity of lambda 1 will be 1, right? Of course, if the algebraic multiplicity was a bigger number than 1, then we will have to check. Right? And the geometric multiplicity of lambda 2 is 1. Okay, but let's now try to find those eigenspace. So let's take lambda 1 equal to. Okay, so to get the eigenspace of lambda 1, I need to get the null space of A minus lambda 1 I. Okay, so recap. What is the null space? The null space, maybe I should recap this up here. The null space of a matrix, the null space of a matrix M is the space of all, or let's say it's just the solution of that, is the solution set, all possible solutions of this equation, M x equals 0. Okay, so you know ax equal b, set the right hand side to 0. So ax equals 0, right? All x values. So first we let's form A minus lambda 1 I. Okay, so A was 1, 2, 2 minus 2, and I'm going to subtract lambda 1 from the diagonal. Lambda 1 was 2. So subtract 2 from the diagonal entries. So this is 1 minus 2 is minus 1, 2, 2, minus 4. Okay, so we need to solve for A minus lambda 1 I x, let's say, equals 0, right? Where, let's say, x is x1, x2 transpose, right? It's a column. So there are many ways you could do this. So the foolproof way, which is you could of course convert this to a system of equations and solve that. But for bigger matrices, that's more difficult to do. So the best way to do this is to use row reduction. Right? Even though for a 2 by 2 matrix, it's straightforward to solve the system of equation, best to get into the habit of practicing row reduction. So this is our matrix A minus lambda 1 I. Of course, what we should be doing is taking the matrix A minus lambda I, and we should be augmenting it with a column of zeros, right, to form the augmented matrix. And this is the matrix that we should row reduce to rational form. But remember, this column of zeros, when we perform elementary row operations on it, nothing happens with this column of zeros. It just remains as a column of zeros. So instead of augmenting this matrix with a column of zeros, let's just work with that matrix, right? So usually folks, they don't even bother adding on that 0 column. They just work with this matrix as is. So I could do, let's say, Row 2 goes to row 2 plus 2 times row 1. Right? And of course, this matrix is not equal to, it's row equivalent to. So row 1 is the same. And row 2 is row 2 plus 2 row 1. So here's 0. 2 by 2 is 4. Here's a 0. Right? So I get this matrix and now convert back to a system of equations, right? So this here represents the x1 and this here represents the x2. So this means we have minus 1x1 plus 2x2 is equal to the right-hand side. And the right-hand side is 0, right? We are solving for the null space. The null space means the right-hand side vector is 0. So we only get one equation, and that's okay because we know the dimension of the space is how many free variables we will have. And we know from before that the dimension of this space is 1. So we are expecting one free variable, right? So we could take, for example, you could take anyone, but we could take, for example, x2 as the free variable. So therefore, x1 is equal to minus, sorry, x1 is 2x2, right? x1 is 2x2. So the eigenspace corresponding to lambda 1 is the set of all vectors x such that A minus lambda 1 I times x equal 0. We just found what these vectors look like. So this is all vectors of the form x1, x2. Okay, so instead of putting transpose, let me write it as a column one time. So this is x1, x2, such that, what's the condition? x1, right? x1 is equal to 2x2. Okay, so let me sub that in. So this will be 2x2, x1 is 2x2, x2, where x2 is any real number. Okay, and now I could pull out x2. So this is just x2 by 2, 1, where x2 is any real number. And what is this? This is just all multiples of 2, 1. This is just the span of the vector 2, 1. Right? And of course, it's a subspace. So the span is a subspace. Right? So this is the eigenspace. This is the eigenspace for lambda equal for lambda 1. Let's see. Right, of course, you don't have to write out all these detailed steps. For example, with practice, you could go simply from here straight to here. That's fine as well. Right? But when you're learning it is, you could get into the habit of writing out all the steps. And what if I want a corresponding eigenvector? Example of an eigenvector is take any vector from this space. Any vector, any multiple of 2, 1. Right? You could even take 2, 1. Right? So this is an eigenvector. Right? So that is, of course, for lambda equal to 2. But we need to redo that proof for the second eigenvalue, 3. Okay, so 4 lambda 2 equal 3. Right, so again, we need to solve for the null space of A minus lambda 2I, which is A minus lambda 2I times a vector. Again, we could use fact x, right? It doesn't matter. Is equal to 0, where of course we know that this x here was different from this x here, right? It's just a variable we were using. Okay. So now let's form the matrix A minus lambda 2I. So again, what is that? That's the matrix A, which was 1, 2, 2, minus 2. And I'm going to subtract 3, minus 3. What was lambda 2? Oh, I made a mistake. Lambda 2 is minus 3, right? Minus 3, minus 3. Okay. So I'm going to subtract off minus 3, which is the same as adding 3. Yeah, same as adding 3. Okay. So that is 1 plus 3 is 4, 2, 2, minus 2 plus 3 is 1. Right, so we could reduce this guy. So we could do again row 2 goes to, oh, we could do row 1. Row 1 goes to row 1 minus 2 row 2 minus 2 row 2. So 4 minus 2 by 2 is 4, which is 0, 2, 0, 2, 1, right? And like before, this is x1 and this is x2. So convert back to a system of equations. Convert into a system of equations gives 2x1 plus 1x2 equal to 0, right? It's always equal to 0. And again, we should be expecting one free variable because we know the dimension of the space is 1. And we could take, for example, x1 as the free variable. Right, so that gives x2 is equal to minus 2x. So the vector x is equal to x1, x2, which is x1 and x2 was minus 2x1, which is x1 into 1 minus 2. Therefore, the eigenspace corresponding to lambda 2 is the span of, right? So this is the short way to do it, 1 minus 2. Right? And an example of an eigenvector is 1 minus 2. Right, so this was an example to figure out, given a matrix, how to get an eigenvalue, the corresponding eigenspace, the eigenvectors, one example of eigenvector for it. Okay, so let's look at example 1. Let's look at one more example with a 3 by 3 matrix. So let's look at this example. Say we were given A as 2, 1, 0, 0, 5, 1, 0, 0, 5, right? And let's just say, of course, it's a 3 by 3 matrix, and let's just say they are real entries. Okay. So again, I want to find for this matrix the corresponding eigenvalues. For each eigenvalue, I want the algebraic, the geometric multiplicity, I want the eigenspace, and I want an example of an eigenvalue for that. So just like before, we need to get the characteristic polynomial. Now, there is a shortcut here. The first thing to do when you're dealing with these questions is to identify whether the matrix A is upper triangular, lower triangular, or diagonal. Because if it is any of those three, the eigenvalues are on the diagonal. These are the eigenvalues, right? That's something we could prove, right? So right away, I could say, since A is a triangular, right? Upper triangular matrix, the eigenvalues are the diagonal entries. Again, and you could see that if you go and you construct the characteristic polynomial of A, and you go and you work out the determinant of A minus lambda I, and you work out this, so this would be the determinant now of a 3 by 3 matrix, right? You'll see that the roots of this is the diagonal entries. Right? So always something to look out for, right? Always be looking out for what is the structure of the matrix, right? So this is the eigenvalues, right? Therefore, lambda 1 is 2, lambda 2 is 5. But notice 5 is repeated twice. Right? So the algebraic multiplicity of lambda 1 is 1, so only repeated once. And so right away, the geometric multiplicity of lambda 1 is 1, right? So we are expecting a one free variable when we solve for that eigenspace. The algebraic multiplicity of lambda 2 is 2. It's repeated 2 times. So the geometric multiplicity of lambda 2 is, we don't know. We can't say yet. We actually have to find this one because it could be 1 or 2. Right? It could be 1 or 2. We don't know which one. Right? We have to see. Okay, so like before, for lambda 1 equal 1, sorry, 2. Lambda 1 equal 2. Right? I need to solve for the null space of A minus lambda 1 I. Right? So let's form this matrix. A minus lambda 1 I. Let's form this matrix. So it's a matrix A, which was 2, 1, 0, 0, 5, 1, 0, 0, 5. That's the matrix A. And I'm going to subtract from the diagonal lambda 1. So minus 2, minus 2, minus 2. Okay. So this is 0, 1, 0, 0, 5 minus 2 is 3, 1, 0, 0, 3, right? And so we just so we could let x, which is the solution vector, be x1, x2, x3, right? Then a minus lambda 1 x equals 0 gives, right? So remember, this is x1, this is x2, this is the x3 column. So now we're converting back to a system of equations. Okay, so we get from the first row. From the first row, I get x. I get x2, 1x2 equals, remember it's always equal 0. When you solve for the null space, it's always equal to zeros. The second row is 3x2 plus x3 equals 0. And the last guy is 3x3 equals 0. Right? So this one tells me x3 is 0. This one tells me x2 is 0. Right? And this one is satisfied. Right? Because I get 3 by 0 plus 0 is 0. Right? But what is x1? Remember, we already know what the dimension of that space is. Right? We already know the dimension of this space is 1. So we are expecting one free variable. The free variable x2 is 0, x3 is 0. Where's x1? X1 is the free variable. Right? So we take x1 as the free variable. This gives, so we know the vector x is x1, x2, x3, right? So x1 is the free variable, x2 is 0, x3 is 0. So this is x1, pull x1 out, 0, 0. Right? Therefore, what is the eigenspace? The eigenspace associated to lambda 1 is the span of this vector. 1, 0, 0. Right? And of course, it's one-dimensional. It's the span of one vector. Right? Where 1, 0, 0 is a corresponding eigenvector for lambda 1. Right, and of course, if you want a second corresponding eigenvector for lambda 1, just take any multiple of this one. So put any value in for x1 except 0. You're not allowed to choose x1 equal to 0 because then you get the eigenvector to be 0. And that can't happen. Eigenvectors are not 0. Right, but pick any other value of x1. And for any value of x1, any non-zero value of x1 you pick, you generate a new eigenvector. Okay, so well, that's the easy case, right? The interesting case is the second one, which is for lambda 2 equals 5, right? Remember, we are expecting either geometric multiplicity 1 or 2, right? So either one free variable or two free variables. We don't know, right? So of course we need to solve for the null space of a minus lambda 2I, right? So that is the same thing as a minus lambda 2I by some vector. We could use the same vector again, okay? Equal 0. So what is this matrix? A minus lambda 2I. Let's form this matrix. All right, so it's A, which is 2, 1, 0, 0, 5, 1, 0, 0, 5. That's the matrix A. And I'm going to subtract 5 from the diagonal entries. Oops. So lambda is 5. Subtract 5. Subtract 5. Subtract 5. Right? So this gives the matrix 2 minus 5 is minus 3. 1, 0, 0. 5 minus 5 is 0, 1, 0, 0, 0 row. Nice. All right. So actually, we don't even need to row reduce this. This matrix is already in row echelon form. Right? This is already in row echelon form. Right? So here's x1, here's x2, and here's x3. So we convert back to a system of equations. And that gives me minus 3x1 plus x2 equals 0. It's always equal to 0. The second row gives me x3 is equal to 0. And the third row doesn't give me any information. The third row is just zeros. Okay. So x3 is 0, right? We know that. So I have one equation here essentially between x2 and x1. So x2 is 3x1. So remember, we were expecting either one or two free variables. So I only have one free variable, right? So you could choose either x1 or x2, it doesn't matter. So let's just say we take x1 as the free variable. Then x is x1, x2, x3, right? x1 is the free variable, so x1 is x1. x2 we found to be 3x1, and x3 is always 0. So this is, so factor out x1, 1, 3, 0, right? So therefore, the eigenspace associated to lambda 2 is simply the span of this vector. 1, 3, 0, right? And an example of an eigenvector is 1, 3, 0, or any multiple of this kind for lambda 2, well, 5, right? And also if you're row reducing to solve for the null space, if you are in row echelon or reduced row echelon form, remember the rank. The rank of a matrix is the number of non-zero rows in reduced row echelon form. So the rank of this matrix is 1 non-zero row, 2 non-zero row. So the rank of this matrix is 2. And remember the rank nullity theorem? So for square matrices, it's very easy to remember because for square matrix, you don't need to remember whether it's the number of columns or the number of rows because they're the same. So actually from here, you could figure out right away what the geometric multiplicity is. The rank is equal to 2, right? Therefore, it's the row by column is the number of columns is equal to the rank plus the nullity, right? But like I said, for square matrices, you don't need to remember. You're lucky because if you slip up and you put the number of rows here instead of the number of columns, it's the same number. So you get the same value. So it's 3 equal 2 plus the nullity. So the nullity is 1. And of course, what is the nullity? The nullity is the dimension of the null space. What is the null space? The null space is the eigenspace. So what is the dimension of the eigenspace? The dimension of the eigenspace is let's go all the way up. Where is it? The dimension of the eigenspace is the geometric multiplicity. So right there, once you are in reduced row or row echelon form, the number, you can immediately get the rank and just do this quick calculation to the side, and it will tell you right away what the geometric multiplicity is. This is the geometric multiplicity for lambda 2, right? And it was one-dimensional, right? This is a one-dimensional space, right? It only has one vector in its spaces. That's the vector. Okay, so those are two examples of given a matrix. How do you get the eigenvalues, the eigenvectors, the eigenspaces, right? And also a recap on the theory behind it.